Okay, so in this video, we're going to see how we can solve, or maybe not really solve, but resolve those paradoxes that we saw in the last video, which was a major problem of the Hamilton method. So what we're going to do here is introduce a new method called the Jefferson method, and I'll take you through the steps for doing the Jefferson method, how it works. I'm going to try to actually simplify the method for us a little bit so that you don't have to worry about everything. The big picture here is I want you to be able to see how the Jefferson method solves those paradoxes that we saw with the Hamilton method. Yeah, so let's take a look. Okay, so I decided to save us a little bit of time here and type out the Jefferson method, kind of the highlights of it, rather than you having to watch me write it all down. So the good thing about the Jefferson method is it's really almost identical to the Hamilton method, with the exception of when we get towards the end here. So just kind of a reminder, right? The Hamilton method, we start off by finding our divisor, which was our total population, divided by the total number of reps that we have, the total number of representatives, right? And this divisor in the Jefferson method ends up sometimes being called the standard divisor, but either way, it's the divisor that we're going to start with, right? We're going to go through and do the same thing we did for the Hamilton method. We're going to find our quotas. That is, we're going to take the state's population for each state, divide by that divisor that we found in step one. And that'll give us a whole number decimal thing that will kind of give us sort of a baseline place to start this process from. We'll do the same thing in step three, where we'll truncate or cut off the decimal parts and just look at the whole number parts. That'll give us what we call the lower quotas. And remember, with the Hamilton method, we added up those lower quotas and we tried to see if we got our total number of representatives. Well, for the Jefferson method, we're going to do the same thing. We're going to add up those total number of lower quotas. And what's going to happen that's different here is, instead of using decimals to figure out who gets like the extra, if we have any extras, we're going to use that feedback from step three, the total from step three. And we're going to say, okay, if that total is less than the total number of representatives, right, then that tells me I have to do something different with my divisor that I started with. Okay, so the key phrase here that's really important for us here is that if the total from step three was less than the number of representatives that we have to apportion, right, we will have to lower the value of the divisor and repeat our process until we add up to our step three again. The number of lower quotas adds up to the total number of representatives, okay? And so this new divisor that we have is sometimes called the modified or adjusted divisor. Now, how much lower the divisor has to be, that's a guess. And this is where this method is kind of inefficient. And I do want to mention this here, is that the drawback here is that what we're really doing is a very guess and check process. We're saying, okay, I'm going to guess that my modified divisor is going to be something lower than my standard divisor, my starting divisor that I had from the Hamilton method. And I'm going to kind of hope that everything works out, but I have to go through and do all these calculations to make sure. So this is pretty time consuming, and it kind of distracts from the purpose of what we're trying to get here out of the big picture. So I want to tell you that in real life, more than likely, this is all going to be done with a computer program or a script or something that's going to run these calculations for you. So you don't have to do this normally. Because of that, I'm going to commit to giving you these modified divisors for the purposes of getting away from wasting your time finding a modified divisor. I just want you to know that when you look for a modified divisor, you're looking for something lower than the divisor we started with, the standard divisor. And I want you to look at the big picture of how the Jefferson method apportions things and helps us out, and how this is different from the Hamilton method that we saw before. So let's go back and take a look at some of our examples that we've seen before, but now we're going to do them with the Jefferson method. So our first example with the Jefferson method is a familiar example. It's the same scenario we had before in the Simpsons case with Bart, Milhouse, and Martin, right? They're buying the Radioactive Man #1 comic book. We know that the number of days is going to be the representatives, right? We're apportioning that. In this particular example, I just want to illustrate how I go about finding the divisors and whatnot, right? So just kind of a quick reminder, this one is the total population is the total amount of money they spent. That was our 35 plus 30 plus 40, which is 105. Our divisor then becomes the 105 divided by 7, which is 15. And then when we find our quotas, right, and our lower quotas, we would do Bart is 35 divided by 15. Millhouse is 30 divided by 15. Millhouse. And Martin, he was 40 divided by 15. Okay. So I went ahead and typed into a calculator, got my quotas for all of these guys. This becomes our lower quotas of 2, 2, 2. When we add these up, we get 6. So we're short by 1, right? So 1 extra is still out there. 1 extra day is still out there. So in the Hamilton method, we would go to the decimals to help inform us who gets the extra. But in the Jefferson method, since we, the question, do we get the number of representatives we started with? No. So with the Jefferson method, we need to get a new divisor. We need to try out a different divisor that's going to be lower than the divisor we started with, which was 15. So no, we need a modified divisor that's less than the original divisor, which was 15. Okay. So I'm going to kind of cheat here a little bit. I know which divisor is going to work, and I know that if you're thinking, okay, if I need to go lower, you might be thinking, well, let me make my divisor 14. It's 1 less than 15. It's less. Let's do that. Turns out if you do 14, it won't work, and then you'll have to go even lower below 14. And turns out that the number that's going to work for us is 13. And remember, I'm going to give you these modified divisors, so you don't have to worry about finding them. You do want to know that it's always going to be less than the divisor we started with, but I will commit to giving you these modified divisors because, again, I want you to see the big picture of how these how this Jefferson method works. So we'll use a modified divisor equal to, oops, sorry, I said 14. I mean 13. We'll use 13, okay? Because again, I've done this problem before. I know this is the one that's going to work. Here's what you'll see. You'll go through and you'll do your step 2 again, because this is essentially our new step 1, but we're going to do the quotas and lower quotas. So for Bart, it's 35 divided by 13. Millhouse, it's 30 divided by 13. And for Martin, it's 40 divided by 13. So quick calculator, and you're going to get, I'm just going to, in this case, I could go out to 3 decimals. I'm just going to quickly round here so that we just can get this over with real quick. 2.7, 2.3, and like 3.1. Because we don't need those decimal parts anymore. This is 2, 2, 3, right? That totals up to 7, which is the number that we were trying to give out, the number of days we were trying to give out. So in this case, this is an illustration where this modified standard divisor of 13, so 13 worked. We know that because we didn't have any extras to give out. Right? We weren't short in terms of giving out the number of days. So answer here was that Bart is going to get 2 days, Millhouse is going to get 2 days, and Martin is going to get 3 days. If you kind of recall, this is the same answer we got with the Hamilton method before, which is totally fine. It's okay for Jefferson and Hamilton to agree. But it's also okay for Jefferson and Hamilton to disagree, and that we'll see a little later with some subtle different examples that we kind of encounter. So let's take a look at another couple of examples of the Jefferson method. Then we'll get into another video with more sort of detailed examples that compare Jefferson to Hamilton. So I'm going to have a couple of examples here. These should look sort of familiar. Like we have a Jefferson, oops, I said plan, I meant method. I'm sorry about that. That should be method. Should be method. So I have a couple of Jefferson method examples. We're apportioning 11 representatives to 3 states, A, B, C, and we have a modified standard divisor or modified divisor of 28. I am giving that to you. So to run the Jefferson method, all we have to do is find our quotas and lower quotas, and really just make sure that this divisor, this modified divisor that we have, actually works here. So let's take a look here. State A, state B, and state C. Go ahead and speed up the video here. So you can see with the Jefferson method, all we do is take our populations for each state, divide them by the modified divisor, look at our decimals, chop off the decimals, and grab the whole number parts. And once you add these up, 1 plus 4 plus 6 is 11. That actually happens to match the number of representatives we were trying to give out. So our answer here, right, is state A is going to get 1, state B is going to get 4, and state C is going to get 6 representatives. Jefferson is kind of easier once I take out the fact that you have that technically in the real world you'd have to find that modified divisor. It's just a verification that this plan works, okay? Okay, we're going to kind of, again, same thing. Let's speed up the video and walk through this next example. And again, you can see our lower quotas, 1 plus 4 plus 6, add up to 11. So this checks out just like the one up above checked out. A gets 1, B gets 4, and C gets 6. So everybody gets, and what's sort of interesting here, hopefully you may look at these two examples and think, gosh, these numbers look familiar, the situation looks familiar. Notice that we have the 3 states, A, state B, and state C, but look at the years that were expressed in these questions. There was the 1900 population and the 1920 population. Notice that the populations have gone up for each state between these different years. This might sound like it's got the potential to be a population paradox, and in fact, it was a population paradox in the last sort of set of videos and when we were talking about the Hamilton method and how it causes these paradoxes. So I want to point out here that when we did the Hamilton method with these that created these paradoxes, we had this example. We had the population in 1900 for states A, B, and C. We got A is 1, B is 2, C is 3. Notice that for the Jefferson method, that first example was the same result, 1, 4, and 6. But in that last example, the reason why it was a paradox is because A ended up getting 2, B got 4, and C got 5 when the populations grew. And the Hamilton method essentially caused this to happen. It kind of messed things up a little bit for us, because basically the Hamilton method sort of stops working at a certain point in certain specific scenarios that we can't predict are going to happen. So here Hamilton messed up, but notice that Jefferson was very consistent. It gave us the same 1, 4, 6, 1 for A, 4 for B, 6 for C, and it didn't have, the Jefferson method did not have the population paradox. So this is an example of how the Jefferson method actually ends up fixing those paradoxes. And we'll take a look in the examples that we see coming up, how the Jefferson method ends up kind of resolving some of the paradoxes we saw last time. So let's take a look.